Well, hi and welcome, and thanks for joining me here in my shop for another session here with this radio. This will be session number 2, and I'm going to start changing some of the parts out in this radio. And I think I'm going to follow kind of the plan I laid out at the end of the last video. Pretty straightforward. We're going to first get rid of the hum. That's got to be this guy. Make the radio a little bit safer by getting rid of this guy and replacing it, replacing this one. And then from there, I think probably doing any capacitors in the audio circuits. And we can listen to what we got at that point, and then we can work on the RF and the radio front end lastly. Then of course it's an alignment. And along the way, who knows what else is going to pop out of here. So I'm going to get busy and deal with this big capacitor here right off the bat. And how big is it? Now, I haven't been able to find a schematic because I can't identify the model number for this radio. The model number is son of a gun if it isn't right here. Oh, it's right here, for crying out loud. Okay, there you go. Wait, now I know the model number. That's fantastic. So I think I'm gonna. Well, and what is the model number, Jim? Looks like EU1 4516. EU1 4516. That's an odd model number. Okay. See if I can find. I'm gonna go see if I can find a schematic right away on this. Well, it turns out I did find the schematic. The model number is actually 4631. That's the real model number. And I think this EU1, you can see a list of them here. EU1, PU1, SU1. These must be different styles of cabinets or something like that going on, including the dictator. I wish I had a dictator. I've only got a Viking. Hey, in fact, I am Viking. According to my grandfather, my background is Viking. Yeah, okay. I don't act like a Viking, though. Now, since I have the schematic, why don't we go over it? I've already been glancing at it, and I want to start with this slightly confusing depiction here, and this note up here, and the way the rectifier tube has been shown. Just a little odd. So what's going on down here is some of these radios come with a miniature bulb, a 6 or 8 volt bulb, using the tap on the rectifier heater. Other radios come with a 110 volt little tiny, Christmas light type bulb. The one I have here has the 110 volt system. So this does not exist in my radio. And if we come up and read this note with 110 volt pilot light connection as shown with dotted lines. 6.8 volt pilot light connect as shown with solid lines. So we look up here, and they've repeated this part of the schematic up here. It's a dangerous thing to do for people like me. Get confused easy. I think they're drawing more attention to exactly how the wiring is done in the radio, where the connections are made to. So this is the rectifier tube, and I looked at this for a while, and there's something missing here. There's only one connection to the rectifier tube here on the cathode. So you look at the plate, and they didn't show any connections from it. It's just an oversight, I'm sure. There should probably be a ground terminal somewhere in here. I don't know where. Maybe not a ground terminal. Like, I don't think it goes back to the chassis. In fact, no, it doesn't, because here's the chassis capacitor and its resistor right here, which I'm going to replace. And otherwise, there's a B- wire or B- bus running through the radio. And they got this resistor bleeding down some of the voltage here in the heater string. Oh, that's interesting, because usually it's a 35, a 50, and then 3 12s. But look, it's a 35 and a 35. So if you add these up, that's 70 and another 36. That's 106. So it's just short of what it should be. It should be closer to 120, or 117 as they're putting it. So this is the dropper compensating for the. So why wouldn't they put a 50L6 in here and do it that way? Why? I don't know. Probably because it was 4 cents cheaper per radio to do it this way. maybe somebody ran into the office afterwards and said, hey, I got an idea. We can save 4 cents a radio if we stop putting 50 L6s in it, use those cheaper 35 L6s and stick a resistor here. Hey, great, Joe, there'll be more in your envelope next week. 3 cents, 3 cents more. So this is a bypass capacitor here, shown way up here. We have a filter capacitor there. This is what I'm going to be replacing. And here, E20, E50, and E10. So it looks like a 10, 20, 50 guy here. It's just 3 of them. Yeah, I don't see any other electrolytic capacitors. So those are the 3 I want to change out. And this guy. And probably his resistor will go too. Make it all nice and new. But yeah, sure, just run through this quickly, because I already see a couple other things that look interesting, like what's going on here with this? Like, why did they show it like this? There's a reason. There's a reason. There's a reason why this is shown looping around like that too. And I don't know. I'm just going to glance at the antenna here. We'll put it on camera a bit. It doesn't look. I don't know. I don't know what they're up to there. I can see this ground point though. Okay, and then we just have your regular tuning of the radio against this antenna, the loop antenna, into the mixer tube. Here's the oscillator circuit here. Coming out, these tubes are shown upside down from what is typical today. So here's the plate. Very low, B plus 78 volts. Going through to the IF amplifier, a 6SK7, just typical tubes here. Nothing spectacular going on. Through the other IF transformer up onto these diodes. Looks like they're using both diodes. These 2 pins are tied together on the tube. There are the 2 diodes in there. The rectified output comes down this way. The audio portion is recovered. The DC is blocked at this point, and the audio is fired off to the grid on the triode here on its way forward through this capacitor. It's blocking the 45 volts, not too much, from the grid here, and out on this is a beam power tube. You can tell by the way they've drawn it in here. And down we come. That's about it. Out from the plate, up through the transformer and back to the power supply, and there's no feedback that I can spot here. Nothing, no humbucking coil or anything. So we'll follow the AVC back now. AVC from here comes down through here. So most of the DC voltage is developed across this 500,000 ohm resistor. That voltage is then supplied through this resistor with no current flowing, or virtually no current flowing. All the voltage shows up here and is applied to these 2 grids. So we're controlling the first 2 tubes, the gain on the first 2 tubes. It's a very, very straightforward 5-tube radio. Winding polarity, I don't care about that. Hopefully I won't have to care about that. Actual B plus looks like 78 volts. Not very much. What's the plate? So we got 110. So you manage to get 110 on the plate of the output tube. Okay, that's pretty straightforward. So this doesn't change my plan at all. I'm just going to carry on. I'll show you this. We'll take a closer look at what are they trying to show here with this weird reversing loop thing. Or did the draftsman just get a little fancy here? Let's go find out. Okay, let's take a look at that antenna here. So here is the wire coming out and reaching the chassis right here. So this is the connection of the funny pull down loop, And if you look at it carefully, you can see that this is actually two wires twisted together here. This is actually a loop being pulled down and grounded. So I think on the schematic where he showed that loop twisted once, he's trying to say it's twisted many times. And if he'd shown it, it's a little hard to do in drafting, neatly, but if he'd shown a couple of turns there, I would have got it. But I didn't get it just from what he did. So, but there it is anyway. So now we know what's up. Isn't it kind of surprising that you'd want to twist a wire this short distance and yet have excess wire? Like, why isn't this right over tight? So almost certainly the antenna is made in one bench and then presented to the guy who's working on the chassis to hook it onto his chassis. Something like that's going on. So they're going to build these with enough wire that there's no doubt it can be attached. That's my guess on that. So, okay, now the capacitors we're going to do is this guy, and you can see the three sections: 10, 20, and 50. So I'm pretty sure this will be the original capacitor, and they got the color code of the wires: red, yellow, and green. And the wires are coming out just down here. So, and the colors remain. One wire is hidden from view up here, so I guess that's red, I guess that's yellow, and the last one has to be green, because often the colors don't really last. Oh, there's a really nice green wire running right here. That's probably the green wire. Hey, this isn't, usually these things are kind of welded in. Look what they did too. How smart are they? They put the wording and left a space for this band to go on it. I wonder how many they made before somebody said, hey, every time we put one of these in a radio, we cover one of them. That made a crunchy sound. So I'm pretty sure you can buy capacitors like this to put in radios like this. I think you can buy them brand new. And I think, well, I bet you they're a little expensive, and I'm not inclined to do that. So the crunching that I'm hearing is the wire insulation on the wires. I'm not so sure I want to wreck that. I want to preserve as much of the wiring here as possible so I can use it if I want. Because the fact is, the space in the radio is where this capacitor is. So when I put in the new capacitors, it's best to stick them right in the same space again, because it's here. And guess what's coming here? All these wires are coming here. So if you cut away all the wires, you're kind of you're not helping yourself too much. Occasionally, I don't think it'd be true of these wires, but you don't want to be relocating some wires in a chassis like this too far or too much. Some radios, the last one I worked on, there was a big warning in the manual, just don't move anything. Put everything back just the way it was. Sometimes that's a little tricky, because as you'll see, and this is not important in this case, but when I go to change this capacitor, the new one doesn't look like this at all. It's a totally different size and everything. And maybe I should do this one below it right away too, because it's there. Where's it gone? Looks like it's just catching a. This is the B minus terminal here, so this one's just coming back to B minus. No, I better leave it. I can do it later, but leave it because that's my plan. My plan is to leave it. So let's cut this guy out. I'm going to get him out, resistor and all. Put a new resistor in. Now, good wire sticking there. I won't forget where this came from. I'm going to leave it hanging out like this. No, I'm going to cut it off. We're going to test it. I'm going to give this guy a test, because I can't forget where it came from. Jim, you got everything on video here too, you know. How can you lose track of anything? Oh, I can. I have that talent. Okay, come on over here and we're going to check this capacitor out. So, just in case again you haven't watched me use this instrument before, this is the first of my videos you're watching. This is a capacitor checker, and the way it works, pretty simple. It does two things. One test is it puts a fairly large or a controlled DC voltage across the capacitor. I better cut this resistor out of here. And then reports the amount of leakage on this magic eye here. So it's a pretty sensitive test. I'm sure there's other equipment that will do a better job than this, but this does a good enough job for me anyway. I've tested so many capacitors, I have a calibration in my head on what's good and what's bad here. So 50 volts, what we would hope is when I apply the voltage, the magic eye slams shut, it closes, and then opens fairly quickly wide, right back to where it was. That would indicate a good capacitor. Just get this okay, we'll have to do it like this. So here we go. So that's 50 volts applied to this capacitor. The eye is not opening at all. So this thing can't measure how bad it is. That's the situation. It's so bad, it's off the scale. So very leaky capacitor. Remember when we looked at this one first, I mean, it's just beat up, right? Big chunks of wax missing. But this is probably indicative of the condition of the rest of the capacitors. No surprise. It would be a surprise if they tested good. Should we really go after? No, I want to. This is a big one. It's a great big one. Why don't we find out what this one's doing? 0.1. I think this is probably on the screen circuits. Let's take a look in the schematic here. So we're looking for a big 0.1. Oh. Yeah. T must be tubular, and it would be on the screen. Let's find a screen line. So we'll grab one here. Here's the screen. Oh, and the plate. 0.1 should come jumping out at me. It could be anywhere on the schematic, I think. 0.1. So this is showing it basically across the so you know what I think this guy is doing? So you have these big electrolytic capacitors filtering filtering the rectified AC that's coming out of here. That's a pretty hard job in itself, and these are really good on the low frequency end of things, the 60 cycle end of things. They're not so good at high frequency though. So if you want to snuff out high frequencies, which you normally do in the radio and different lines, then you need additional capacitance of a normal type, not electrolytic, that'll function better at the higher frequencies. This would be the guy. So he's really a brother of these guys. So yeah, he's got to go too. They all got to go. 2, 3, and the safety one, and T1. Yeah, let's do them all. We'll do this one too. But I think if I don't do this, I don't think there would be a hum problem, but there could be other feedback sort of issues here. And if this thing's really, really leaky, I'm sure that's not helpful either. Okay. Okay, we'll cut them out. And up here to the ground. Oop. Now this one looks to be in pretty good shape. This is the polar opposite of the last one. It's interesting. 400 volt, 0.1. Arrow box. This looks to be in about as good a shape as a capacitor can be, at this age. Yeah. Okay, let's go put them in the tester. Okay, let's give them a test here. Okay, so we're going to apply 50 volts and ask the question, is there too much leakage for this eye to stay open? I guess that's the question. Here we go. And it's coming open a little bit. Okay, well, that's not very good. If we put it up to 150 here, I can't imagine. I mean, it can't possibly open. So, as capacitors go, this isn't the worst. But considering that it looks to be in good shape and yet isn't, it says something about, maybe this radio spent 30 years in a damp basement. You have just no idea where. You have no idea where I spent. I spent 30 years in a damp basement, for crying out loud. So, nothing terribly surprising there. I'm going to replace all those capacitors, and then we're going to operate this radio. Let's see what happens. Yeah, I've decided to take a moment and just double check the calibration of my machine on the assumption that a brand new capacitor is going to be accurate. So that's a brand new 0.25 microfarad capacitor. So first the leak test, 50 volts. I see the eye comes wide open, right? Sometimes I wonder, I test so many bad capacitors, I start wondering if my machine's gone bad or not. Here we are. Pretty high voltage, 250 volts, and it comes wide open. I'm just going to give it a moment to discharge the capacitor, then we'll measure its capacitance. Okay. Put the, should be the right scale here. So now I swing the dial till the eye pops open. Open it up maximum. A little bit of dirt on the control, I guess. Ooh. There we are. Now I'm going to get right down here and read this very carefully. So, there's the 0.5 right there, and that's 0.1. The scale is extremely non-linear at this point. So I guess we'll follow on the outside here. 0.1, that's 0.2, that's 0.25. I mean, it's right there. It's right on the money. Even at the top edge of the scale. That's great. You know what I'm going to do now? I'm going to go ahead, I'm going to test one of these big guys here. Little big guy. 22 microfarads. I'm going to get the polarity right this time. Yeah. Follow the conventions. Save you from yourself. There's really no use doing, oh yeah, let's do the leakage test for sure. Brand new electrolytic. What does it look like? Now there's a control here for electrolytic. I have to turn this, and it desensitizes the eye because all electrolytics leak a bit. This gives you a more realistic test. This is a 400 volt, and we're going to do it right on 150 volts right away. Just jumping right there. Boldly go. You see it open right up, wide. Okay, now I'm going to give that one a minute to, not a minute, but about the same length of time charging it to discharge it. And this machine, when you let go of this spring-loaded control, it puts the capacitor, it puts a short on the capacitor. So. Okay, I'm pretty sure that'll be dead by now. Let's go to 0.1 to 50. That would be it. 22 is in there. Let's find 22 on here now. Oh, right there. Anywhere else? If I can go anywhere else, I can't. Almost the same spot on the dial. Well, okay. Make a very accurate reading. Let me get my specialized pointer here. So 50. So it ends with here's the 50. And 50, that's 10, 20, 30, 20, 10, 20. So 20 is there. So that's close again. 22 would be just a little higher. About like that. Very good. That's good enough for me, for sure. Because, you know, in a repair situation, what you're looking for are gross defects. You're not looking for a 5% problem. You're looking for a 500% problem. Okay, that's all done. I think now it's just a matter of actually doing some real work in here. Okay, I think I'm just about ready now. Let's take a look what we've got here. So I've left this black wiring here unnecessarily. Okay. And we go down below here. Got the little tiny replacements for the. So I'm looking for accidental shorts, wires exposed that maybe. Come on, camera, you can do it. So I just spliced into the existing lead wires here. Looks pretty good. I think we can turn this guy on now. That's what I think. So hopefully those changes have eliminated the hum that's in the radio. We'll have a better chance to hear how it works. Now there still is the broken wire on this coil up here, so there's lots of reasons to think this radio just cannot really work. Okay, switch is off. Plug is in. Okay, I don't think there's anything more. I don't think there's nothing to wait for, Jim. Just power on. Good. Now I don't remember that this light even worked. Let's see if it works here. Switch on. Yeah, that light's burned out. Okay, tubes are warming up. Wow, took a long time to warm up. So there was a hum there for a moment. That kind of hum. And you see what I'm doing. I'm moving the volume control. So what I believe is happening is where the volume wiper slides over, there's dirt there, and sometimes it's not connected. As soon as it disconnects, then the audio amplifier is hooked up to this. Nothing more, because this is now dirty, and this is the radio signal coming. If you like the radio audio, this is the slider picking it up. As soon as it lifts up, this becomes high impedance, becomes an antenna, and it's going to pick up hums and all kinds of weird stuff. You're going to hear it at the audio frequency because that's what we're listening to, right? So clean that and that'll all go away. There, right. In fact, let's do it right now. Why not? Why not? So I look for a place to spray some, in my case, WD-40 in here. Sometimes right past the terminals there's gaps. Other times there can be holes in the box here. The back part is the on-off switch. The front part is the part we're interested in. Going in here. Just going to blast it. Yeah. Didn't work. Try it again. I'm sure I see a gap there. Good. Okay. What do we hear? We hear the sound I said was because of the thing is lifted. Let's not bank on that. Mr. Radio, will you work now? Turn it down there. Station's down around here. Okay, we should start picking stuff up. So that sports station is pretty certain to be 590. It's very close to 590 here. Fixed. Done. We're done. No, we're not done yet. Isn't that amazing how well, I mean, the radio works okay. And it's still got all these horrid capacitors in it that we know are bound to be leaky and really not be operating at peak efficiency. Yet the radio can work. Amazing, eh? Good. So on the next video, I'll go after the capacitors in the audio section of the radio. And we'll see how that goes. And maybe I'll go after all the capacitors at that point. And who's showing up right on time? Mr. Peanut. Meow. Yes, he wants to get his daily video shot. Well, Mr. Peanut, what are you doing today? What do you want to do? What, you want to come up here? What, you show me? Peanut. Peanut. Hey, what do you want to do today? That was his ears went back. That's his way of saying back that way. What he's trying to get me to do is to go into our rec room, lay on the couch or sit on the couch, and he jumps up on my lap and gets, yeah, I turn my back to him, and get a really good head rub, which he loves, which I'm going to go do, because this went fairly well. Thanks a lot for watching, and tomorrow we'll just carry on with this guy.